China's new material just replaced wood forever, and it started with a plant nobody in construction ever took seriously. Right now, engineers have built a bridge out of this material strong enough to carry actual trucks across a river. You heard that right, a truck-bearing bridge built from something once nicknamed the poor man's timber. Picture your car rolling across a crossing built almost entirely from crushed and repressed grass fiber. But the bridge is not even the real story here, and that is just the beginning, because the same material regrows to harvestable height in under 10 years, something no hardwood forest on Earth can match. Stick around, because the reason engineers ignored this for 100 years is stranger than you would guess. Hit a quick like and subscribe so you don't miss the next one. By the end of this video, you are going to understand exactly how this plant earned its way into real building codes. Wood earned its place at the center of human construction the honest way, through 10,000 years of trial and error that nobody could fake. Engineers love wood because it is light enough to lift by hand, yet strong enough to carry a roof for a century. Manufacturers love it because a single tree yields lumber, pulp, and fuel with almost nothing wasted in the process. Governments love it because a local sawmill can supply an entire town's worth of homes without waiting on anything more exotic than a forest and a saw. That combination of workability, strength, and sheer familiarity is why wood framed nearly every house, barn, and bridge built before the 20th century. Picture a carpenter with nothing but a handsaw and a plane, and in a single afternoon, that carpenter can shape a beam that will hold weight for 80 years. Here is the detail that makes wood's dominance even more impressive. It grows itself, using nothing but sunlight, rain, and time, requiring no factory, no furnace, and no chemical process to become load-bearing. Now, here is the part that most people never stop to consider. Every single plank in a modern lumberyard represents decades of patient, unglamorous waiting that started long before the tree was ever marked for harvest. A forest planted the year a child is born will barely be ready to frame that same child's first house by the time they are raising children of their own. That single fact, more than any other, is what eventually forced engineers to stop asking how to grow trees faster and start asking whether trees were even the right question at all. So if wood does its job this well, the honest question worth asking is why anyone would spend decades chasing an alternative. Why didn't anyone solve this sooner, if the limitation was standing in every forest the whole time? That question sits at the center of one of the most overlooked material science stories of the last 40 years. Because for all of wood's brilliance, it was quietly running up against a hard biological limit that no amount of clever carpentry could fix. Consider what that limit actually means at a global scale. The world now adds roughly 80 million new housing units of demand every single year, a figure comparable to building an entirely new Germany's worth of homes annually, and no forestry program on Earth can plant its way out of that math. Wood built our world for 10,000 years. It could never build it fast enough. The vulnerability inside wood is not a manufacturing defect. It is a biological ceiling written into how trees grow in the first place. A tree strong enough to use for real construction takes between 25 and 75 years to reach maturity, meaning a sapling planted today will not be ready to build with until your grandchildren are grown adults. This is not about wood being a flawed material. It is about wood being a material borrowed from a clock that runs on a scale no construction industry can wait for. Cities are adding roughly 70 million new residents to urban areas worldwide every single year, a population increase larger than the entire country of France, arriving in cities annually, and forests simply cannot regrow at anywhere near that pace. So builders turn to steel and concrete instead, materials that pour and weld on demand. But together, Those two materials now account for more than 15% of all human carbon dioxide emissions, a share larger than every car, truck, and airplane on Earth combined. Here is the trap that took decades to fully see. The slow material is gentle on the planet, but cannot keep up with demand. The fast materials can keep up, but are actively hurting the planet they are built on. Think of it like choosing between a bicycle and a delivery truck, when what you actually need is a bicycle that can carry a truck's worth of cargo, an option nobody believed existed. For almost 4 decades, that exact possibility sat unexplored, dismissed before anyone seriously ran the numbers. There was no third option, and every builder on the planet had quietly accepted that as the permanent state of construction. Here is the detail that puts everything into perspective. Even the most efficient forestry operations in the world cannot compress a 75-year growth cycle down to a decade, no matter how much fertilizer, irrigation, or genetic selection gets thrown at the problem, because trees are simply not built to sprint. For almost 4 decades, that biological ceiling sat there quietly, accepted by engineers as an unavoidable fact of nature rather than a problem waiting for a solution. Most people never think about where their floor joists actually came from, or how many decades passed underground before that beam was ever cut. In 1987, a team at Nanjing Forestry University began answering that question with data that was harder to dismiss than anything the field had seen before. The breakthrough came out of Nanjing Forestry University, working with an overlooked plant that most engineers had already written off. The core idea sounds almost too simple once you hear it. Instead of treating this material like wood, cutting it into neat boards the way a lumber mill would, what if you crushed it down into raw fiber first, the same way a mill grinds wheat into flour before anyone bakes bread with it? Earlier attempts to use this plant structurally failed for one specific reason. Builders kept trying to use the whole stalk directly, hollow, round, and inconsistent from one cut to the next, which meant one piece could be remarkably strong, while the piece right next to it split under the same load. Nailing straight into the stalk almost always caused it to crack down its length, and left untreated, it rotted within a handful of seasons, drawing insects looking for an easy meal. The new approach solved that by fiberizing the entire stalk into loose strands, then drying, resin soaking, aligning, and pressing those strands under extreme heat and pressure until nearly all the air disappears. Here is the part that changes everything about how this material behaves. Once the original stalk no longer exists as a shape, every one of its old weaknesses, the hollow center, the round profile, the uneven strength, disappears along with it. Here is the part that changes how you should picture this material entirely. It no longer resembles a plant at all once it leaves the press, looking instead like a dense hardwood plank, uniform in color and grain, indistinguishable on a job site from oak or maple, unless someone tells you otherwise. Run your hand across a finished sample, and you would swear it came from a 100-year-old tree rather than a grass harvested last season. What comes out of the press is dense enough to sink in water and hard enough to outperform most hardwood flooring sold today. This is new. The process wastes almost nothing, using roughly 80% of the original plant, including the bent and low-grade pieces that would normally be discarded entirely. That transformation, from a hollow, unpredictable stalk into a dependable manufactured plank, is the entire reason this material could even be considered for a building code in the first place. The question that remained was whether a manufactured material this consistent could actually survive a real construction site. The primary limitation researchers had to confront first was strength variability at the microscopic level, since the natural fiber itself still carries small imperfections that no amount of pressing fully erases. But here is what that number actually means in practice. High-quality output has tested with compressive strength exceeding 23,000 pounds per square inch and bending strength climbing past 43,000. numbers that place it well inside the range of premium engineered hardwood rather than anywhere near its old reputation as scaffolding material. To put that in perspective, that is roughly the load-bearing performance you would expect from the hardwood flooring in a luxury home, except grown from a plant that regrows before a single child finishes elementary school. For nearly any residential application, where load requirements sit far below a material's theoretical ceiling anyway, that microscopic variability becomes functionally irrelevant to anyone actually living inside the finished structure. In practice, the beam in your ceiling never needs to survive its absolute maximum rated load. It only ever needs to survive what actually happens in daily life. And this material clears that bar with room to spare. Here is the unexpected advantage that surprised even the original research team. This material regrows to full harvestable height in under 10 years without needing to be replanted at all, since the root system stays alive underground and simply sends up a new stalk after every harvest. That regrowth advantage opens a non-obvious application already happening today, supplying construction-grade material to regions with degraded soil where slow-growing timber forests would take generations to re-establish themselves. The honest picture is a material with small, manageable inconsistencies at the fiber level that manufacturing already compensates for, paired with a renewal speed no hardwood forest on the planet can match. Here is what most people get wrong about materials like this one. They assume strength is the hard part and speed is just a bonus, when in construction, the opposite is often true, since a merely adequate material that regrows in a decade can outcompete a superior one that takes a lifetime, simply because supply can actually keep pace with demand. That single shift in framing, from chasing maximum strength toward chasing dependable renewal, is what quietly separated this material from every other wood substitute that came before it and failed to scale. The question was no longer whether this material worked. The question was how high a building the world was willing to trust it with. That question got answered with a 7-story building in China, recognized as the tallest structure built primarily from this engineered material, with its columns, beams, and floors entirely prefabricated before ever reaching the construction site. To put that height in perspective, picture an ordinary apartment block, the kind you would walk past without a second glance, standing entirely on beams pressed from processed plant fiber instead of steel or timber. Field monitoring recorded structural performance within a narrow margin of laboratory predictions across a full year of occupancy, including humid summers and freezing winters that typically stress traditional building materials the hardest. The field matched the forecast. That distinction matters enormously in construction, because a material can look flawless in a lab and still fail under years of real moisture, vibration, and thermal cycling that no test chamber fully replicates. One engineer who has spent decades working between universities in China and the United States also used this material to build a road bridge in Hunan province, assembled in about 1 week by a small team using no heavy construction equipment at all. Picture a crew smaller than a soccer team raising a truck-rated bridge in the time it takes most crews to pour a single concrete footing. As one engineer involved in the bridge project told local media, quote, "This is the first time we have watched a lab number survive contact with an actual river," end quote. If a bridge built from processed plant fiber carrying real trucks across real water surprised you, the next part is going to be even harder to believe. Hit subscribe so you're there when we cover it. It started with one application where speed and weight mattered more than upfront material cost. Then it spread outward from there, into parking structures, footbridges, and now full residential buildings. Local inspectors who once dismissed this material as scaffolding grade now sign off on it for load-bearing columns, the same signature that used to be reserved exclusively for steel and treated lumber. That shift in who is willing to put their name on the paperwork is quietly the most important development in this entire story, because a material can be strong in a lab for decades and still go nowhere without that signature. Getting that signature took nearly 40 years of accumulated testing before a single inspector was willing to risk their license on it. The claim now had receipts. More than 100 research institutions worldwide now cite this fiber alignment binding process across nearly 7,000 published studies in the 10 years leading up to 2024. A volume of research larger than what most established building materials accumulate in twice that time. These are not academic citations. These are legal and financial commitments, the kind that only follow once an industry believes a material is heading toward real commercial deployment. China's own government backed a 3-year national plan to scale this material as a substitute for steel and concrete, setting up demonstration zones across the country specifically to prove the industry could work at massive scale. China holds roughly 1/5 of the entire world's supply of this raw plant, and it has already built an industrial chain running from forest to factory to finished building beam, a supply advantage no competing country currently matches. A separate initiative launched jointly with the International Bamboo and Rattan Organization carries the explicit goal of replacing plastic and high-emission materials with this plant-based alternative across multiple continents. China's bamboo industry alone carries a stated target of reaching 700 billion yuan in value by 2025 and a full trillion yuan by 2035. Numbers large enough that competitors in India, Vietnam, and the United States have already begun licensing negotiations of their own. In any market where a material offers comparable strength, faster renewal, and a lower long-term carbon footprint, a 10-year regrowth cycle is not a curiosity. It is a competitive pressure no serious construction company can afford to ignore for very long. Independent testing data behind these performance claims has been submitted to open international standards bodies, allowing engineers anywhere in the world to verify the underlying numbers rather than relying on manufacturer claims alone. Here is the detail that puts the scale of this shift into perspective. When researchers recently mapped every company worldwide producing structural versions of this material, roughly 2 out of every 3 were based in China. But new entrants are now appearing in India, Indonesia, Vietnam, and Singapore, with South America's own giant bamboo species drawing fresh interest as an export crop. The technology is spreading outward the same way every real industry eventually does, one licensing deal and one demonstration project at a time, following the exact pattern that solar panels and lithium batteries followed a decade earlier. Analysts project this material could displace a meaningful share of timber and light steel framing across mid-rise construction in the coming decade, a shift roughly equivalent to returning millions of acres of slow-growth forest to uncut wilderness. To put that acreage in perspective, that is an area larger than the entire state of Vermont left standing instead of harvested. Beyond the direct material savings, the plant absorbs and stores carbon while it grows, with China's own reports estimating its forests of this plant lock away around 300 million tons of carbon every single year simply by existing, a figure comparable to the annual emissions of a mid-sized industrialized country. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. Building codes in most countries require years of accumulated performance data before regulators approve a new structural material for occupied buildings. Manufacturing this material requires fiberizing machines, resin baths, and heavy hydraulic presses that most regions with abundant raw plant supply simply do not have built yet. Presses that can each cost several $1,000,000 and take years to install and certify. Only about 1/3 of companies producing structural versions of this material currently publish clear strength data, leaving architects with real gaps in the information they need to specify it confidently. Here is the brutal catch that keeps this from moving faster. The places that could benefit most from a cheap, fast-growing building material, regions with abundant wild plant supply but no industrial base, are often the furthest from the equipment needed to actually process it, meaning the raw resource and the manufacturing capacity to use it rarely exist in the same place yet. Closing that distance is not a science problem anymore. It is an investment problem, a training problem, and a policy problem all at once. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as a manufacturing one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the housing crisis demands is a different question entirely. The story of this material is ultimately the story of what human civilization can build and where it can build it. Right now, the regions that stand to benefit most from a fast-growing, low-carbon building material, parts of Southeast Asia, South America, and Sub-Saharan Africa, are also the regions furthest from the industrial base needed to process it at scale. That gap is not a failure of the plant, it is a failure of infrastructure, and closing it will determine whether this material reshapes construction worldwide or stays concentrated in the handful of countries wealthy enough to build the factories first. Not a boutique eco-material, not a curiosity for garden pavilions, not a footnote in a sustainability report. It is a genuine structural successor standing in for timber in real occupied buildings today. What is genuinely new here, not incrementally better, but categorically different, is a plant-based material that matches engineered hardwood in strength while regrowing on a timeline measured in years instead of generations. That is not a minor improvement. It is a different category of solution. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the construction industry's carbon targets demand is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. Materials like this compound in importance over time, because every building built today using the old default material locks in decades of demand on forests that take a lifetime to replace, which is exactly why the choices being made in demonstration zones and pilot factories right now carry weight far beyond the buildings they currently support. If watching wood's 10,000-year monopoly finally get challenged raises a question about what else might be catching up to concrete and steel, that story is worth understanding too, and it is the subject of our next video. China's new material is 500% stronger than concrete and costs 40% less. The link is in the description. If this changed how you think about the walls around you right now, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every week. Now, I want to hear from you in the comments. Do you think slow-growing timber nations will adopt this material fast enough to matter? Or will fast-growing tropical regions leapfrog ahead of them entirely?